Good morning, everybody, or good day. I guess it's morning right now. Okay, so we are kind of getting into the heart and soul of this chapter, which is all about writing proof. So we're learning all this logic in order to be able to prove something's true, and that their end goal at the end of the chapter is to write a proof. Okay, so this first lesson's kind of wonky. It's kind of weird, and it's nothing really like you've done before, and it's nothing like the rest of the chapter that we've seen. So bear with me. Okay. We're going to talk about a lot of random things. So, the first thing is a postulate or axiom, and that is a statement that is accepted as true without proof. Without proof. We don't need to prove it, we just know it's true. Someone a long time ago proved it, so we don't have to prove it. Someone else did that for us, okay? So, here we go. Our point, line, and plane postulates. So through any 2 points, there is exactly one line. So our picture is describing that for us. I have 2 points here, P and R, and I can draw a line through them. So through any 2 points, there's one line that can be made. Through any 3 non-collinear points, they have to be non-collinear, there's exactly one plane. So in our picture here, we have 3 points, A, B, and C, and they form plane K. Do you guys agree that we can't draw a straight line through any of those points because they're non-collinear? Okay. A line contains at least 2 points, right? We need 2 points to draw a line, so these two kind of go hand in hand, that first one and the second one. They're kind of opposites of each other. Line N contains points P, Q, and R. It has at least 2 points. A plane contains at least 3 non-collinear points. Now this one and this one kind of go together, right? They're just kind of opposites, kind of like the converse of each other. We just kind of flipped it, the order of the wording. So again, if we have a plane, I know for sure there's at least 3 non-collinear points in there. If 2 points line a plane, then the entire line containing those points are in that plane. So if I have some line in here, remember it goes on for forever and ever and ever. And so does a plane, even though I know it kind of looks like it starts and stops, but a plane also goes for forever and ever and ever. So if I have a line on that plane, all those points in that plane or on that line are also in that plane. Okay. If 2 lines intersect, then their intersection is exactly 1 point. So I have 2 lines, S and T here, and they're intersecting at a singular point, P. And then lastly, if 2 planes intersect, then their intersection is a line. So in this example here, we have our planes F and G, and they're intersecting at line W. So some of these things we've kind of mentioned earlier in chapter 1. Some of them maybe we haven't. But refer back to these postulates throughout this assignment, okay? Because on this next page, so if you flip over your notes, we have to use those postulates to describe what's happening. So I know this isn't a great picture. It'd be better if I was using my smartboard, but my room is being used right now, so we're just making this work. It says, explain how the photo illustrates each statement is true. Then state the postulate that can be used to show each statement is true. Okay. So basically, we're going to look at the picture with this given description and then decide which one of our postulates it's demonstrating. So if we look here, line N and line P intersect at point D. So in the picture, we can say that the edges of the building represent lines. So let's say that the edges of the building represent lines. Okay, so that's how our picture's working for us. And now, what postulate talks about 2 lines intersecting at a point? That would be, okay, I'm going to switch over now, folks. This one right here. If 2 lines intersect, their intersection's exactly 1 point. So that's what we're going to write. Okay. So this is true because we know if two lines intersect, they intersect in exactly one point. Two lines intersect in exactly one point. And I know, folks, this seems redundant till I have to repeat yourself or explain why, but that's the whole point of a proof, is like you're not allowed to say anything unless you have a reason to kind of back you up. So like this is our reasoning as to why we could say the building edges represent lines. Okay. Okay, so this next one, it says points A, B, and D form a plane. So do you see A, B, and D? Do you agree that they're not all on the same line on that face of the building? So they do form a plane. So we can say A, B, and D are points on the face of the building, which represents a plane. Which represents a plane. And now we're thinking, what one of our postulates here works with that? So we're looking, which one talks about 3 points making a plane? I sent it in the email to Paula.
Oh, I'll let her know.
Yeah. If not, give me 2 minutes. I'm almost done with this. Hopefully you're thinking this one right here. A plane contains at least 3 non-collinear points. So that's why we can say that. So a plane consists of 3 non-collinear points. Okay, then this last one, the plane that contains A, D, and E intersect the plane that contains F, G, and E in line K. Kind of a lot going on there. So let's find this plane first. ADE is right here. So this front wall of that building intersects EFG, this wall here. And they're saying it makes line K. Again, the 2 faces of our building represent planes. So we can say the 2 faces of the building represent planes. And now we're going back to our front sheet. Where does it talk about planes intersecting? Well, we know right here that if 2 planes intersect, they make a line, which would be our line K. So 2 planes intersect in a line. So again, the whole point of this exercise was us finding in the building what represented a point, line, and plane, and then figuring out which postulate proved that to be true. What postulate made that statement true? Okay, we will finish up the rest of these notes in class when I see you next. Thanks for tuning in.